evening, everyone. First of all, can I just do a sound check? Because I've decided not to use a microphone. Can everyone at the back especially, can you hear me okay? Yeah. Is my voice carrying? Okay. First of all, I'm delighted to be back at Long Eaton. I came as part of the opening for the Malcolm Harry Observatory, and I also came back a couple of times during that year, but having been away for 2 years, it's a really great opportunity for me, and it's a real privilege to be invited back to speak to you tonight. But I must start with an apology, because if you were here for my lecture 2 years ago, a lot of this stuff is going to be the same. So for those of you who were here, there's going to be a lot of Groundhog Day moments, and I apologise for that. But I have got some updates. And what I really want to look at over the next sort of 45 to 50 minutes, with some time for questions afterwards, is the answer to this question or this statement. I want to look at, what have we achieved in the last 58 years since the dawn of the space age? What difference has space science made to our understanding, not only of our place in the universe, but our understanding of planet Earth itself? I want to look at whether space science can actually save life on planet Earth. And finally, I want to finish with some personal reflections about science, and about the future, and about all of the opportunities that are available, especially to the young people in this audience who, by coming tonight, they've shown they've got an interest in astronomy, you've shown you've got an interest in science, and I just want to give you a few ideas of the amazing discoveries that have happened in my lifetime, but more importantly, the amazing discoveries that you can take part in the future. Now, if I'm going to talk about space, of course, the first question is, where is the internationally accepted boundary of space? Where does space actually begin? And the answer is much closer than most people realise. Space is only 100 kilometres away. That's 62 miles. That's less than the distance I've just driven from Bedford, from my last meeting, to get here tonight. The problem is, it's 100 kilometres straight up. And if we want to get up there, we've got to battle against the force of gravity. If we want to stay in space, then we've got to deal with environmental conditions, temperature, pressure, radiation, that are much more challenging than anything we have here on the surface of the Earth. So when we see a view like this, which is a dream-like view, this was actually taken by a NASA astronaut in 2005, and this is the underside of the Space Shuttle Discovery. These are the thermal tiles. Forget about what you read in the media with the idea of holidays in space and Virgin Galactic and so on. It's not tens of thousands of people who've been into space. It's not even 1,000. The total number of people who've ever had this view would fit into one jumbo jet. It's only 550 people. And of those, 19 have died in the process. And the reason is, getting into space, even though we've been doing it for more than half a century, is still pushing our science and our engineering to its very limits. What I'm going to do is we're going to use this whoosh bottle to show the principle by which every rocket that we use to launch satellites actually works. Now, for this particular rocket demonstration, and don't worry, I'm not going to fire this across the lecture theatre. What you need for any rocket is you need a fuel, and I'm going to use ethanol, and you need what we call an oxidizer, something to unlock the chemical energy of this fuel. And the oxidizer for this rocket is just going to be the oxygen in the air in the bottle. Just to talk a little bit more about the history of rockets. Can you put your hands up, please, if you've ever fired a firework? Okay, that's most of you in the audience. If you fired a firework, you've effectively been, what the media call a rocket scientist. I'll save that for the actual firing. Rockets go back a long time. They've been used, they're developed by the Chinese as fireworks more than 1,000 years ago. And those fireworks are what we call solid rockets. Now, solid rockets are great because you haven't got any liquids to mess around with. They're really cheap to make. You can store them for long periods of time. You get loads of energy out of them. And most importantly of all, they make loads of noise. There is one problem with solid rockets, though, with fireworks. And that problem is, once you light them, you can't turn them off. And that's been a real problem, especially in the human spaceflight program. Some of you, especially parents, you might remember the first space shuttle that was destroyed just a minute after launch, killing 7 of its crew. That was because of a problem with solid rockets. So this rocket is a liquid-fueled rocket. And liquids are great because liquids you can control the flow of. I'm stalling for time. I'm shaking for about half a minute, so I'm going to shake for a little bit longer. And liquid fuel rockets come with all sorts of fuels that we use. Some of them use hydrogen and oxygen, some of them use kerosene and oxygen, some of them use dinitrogen, tetroxide, and all sorts of other chemicals as the oxidizer. Solid rockets, like the giant white ones on the side of the space shuttle, actually used aluminium as the fuel and ammonium perchlorate as the oxidizer. So if you're into chemistry, there's all sorts of avenues open for you in rocket engineering. Having done that though, I think I've converted most of this into a vapor. Now what I'm going to do is I'm going to pour off any remaining liquid, I'm going to seal this bottle up, I'm going to turn off that slide, and then I'm just going to apply a flame to the neck of the bottle. 10-12 millilitres of ethanol in there, a tiny amount. Just going to light the splint. Jim, if you don't mind doing the honours with the lights, please. And I will turn off the slide. So, 3, 2, 1. Well, that got your attention. Thank you. I mean, you saw a very dramatic display there of what happens when a tiny amount of ethanol fuel, that was about 1 tablespoon, 12-13 millilitres, had changed into vapour. You can see very dramatically the sorts of energy releases that we are having to deal with. But that was absolutely tiny. When it comes down to the sort of rockets that we use, the majority of any rocket, more than 90% of any rocket, is actually its fuel. And when we're looking at rockets to launch satellites, many of you have been to the National Space Centre, I know. Our rocket tower is about 150 feet high, so our rocket tower is about the same height as a fully fueled space shuttle stack. This is the most successful rocket that ever flew in human spaceflight. It's called the Saturn V. It was used between 1968 and 1972 to get humans to the moon, and it was used for a year before and a year afterwards also to launch America's first space station. But I want to draw your attention to this because this is the height of a 36-floor building. It's 3,000 tonnes fully fueled up, of which 2,900 tonnes were fueled. All of this was used up in the first few minutes to get this tiny capsule to the moon and back with its crew of 3 astronauts on board. A number of Saturn V's were left over at the end of the Apollo program, unused, and just to give you an idea of scale, there's the Saturn V, look at the engines, the F1s, and there's me next to one of them. Now, you compare the drama of this with 10 millilitres of ethanol, and you compare the drama of thousands of tonnes of fuel, you are trying to control an incredibly powerful reaction to blast you at a speed of 5 or even 7 miles every second. Because if you want to go into space and you want to orbit the Earth, like the International Space Station, we need to be travelling at a speed that would get me from here to London in less than 20 seconds. So hopefully you understand the challenges that we have with rocketry. You know, space is not easy. So what have we done since the birth of the space age? Well, this is what started it all. The world's first satellite, Sputnik 1, came out of the Cold War, that battle between the United States and the Soviet Union to try to convince the rest of the world that they were the best. And the Americans were absolutely shocked when they lost round 1. Because this Soviet satellite, I mean, it doesn't exactly look high-tech. All it had in it was a radio transmitter and some cadmium batteries. And all it did was go beep, beep, beep. But of course, while it beeped, it was falling around the Earth in an orbit 16 times a day. And every one of those days, it was passing over the Americans' territory, and there was nothing they could do about it. So this is what triggered the space race. And although the Americans also lost round 2, when Yuri Gagarin became the first human being into space, they pretty soon accelerated ahead. And of course, when President Kennedy made his iconic speech, his challenge to the nation, to get a human being to the moon and return them before the end of the 1960s, the scientists and engineers knew it was possible, but they knew they'd be pushing things to the very limit. And in terms of what we did, in the 1960s, there were loads of firsts. The first woman in space, Valentina Tereshkova. The first spacewalk, going out in spacecraft in a spacesuit, Alexei Leonov. The world's first multi-person spacecraft, Voskhod 1. All of this was to try to build the skills that were necessary for humans to be able to explore the moon. And of course, the Americans won that race. And what strikes me now, I was 4 years old when the last of these landings happened in December 1972, and I remember watching it on TV. Those humans who went, the 12 who walked on the moon, are the only members of our species who've ever walked on an alien world, because that's what the moon is. Next time you look at it up there, it's an alien planet, effectively. And we stopped doing that more than 40 years ago. Why? Because we changed our focus. Instead of wanting to explore, we wanted to start building space stations. We wanted to start doing science in space. We wanted to see what happens for human beings to spend longer and longer in space. And of course, that is what led to the development of the space shuttle. Then in the 1990s, the old Cold War enemies, the Soviet Union fell apart, we had Russia. Russia and America started to cooperate properly. And if you'd have told me when I was at university in the 1980s that I would see the Mir space station docked with an American space shuttle, I would have said, that is crazy. And yet the cooperation began. And all of this led to the building of the International Space Station. Now, there have been more than 30 missions launching all of these separate modules into space. And many of these modules, including, for example, the European Columbus module, they only met with the rest of the station once they were orbiting the Earth. They never met on the ground. So building this while it's travelling at 5 miles a second was an amazing challenge. This is a lovely view of the International Space Station. It's now the size of a football field. And what I love about this particular image that was taken during one of the last shuttle missions, STS-130, is how different the astronaut experience is nowadays compared to the 1960s. Because yes, there are still test pilots there, but we've got people with backgrounds in engineering, in Dottie Metcalf-Lindenberg used to be a science teacher before she was selected by NASA as an astronaut. And what we're now seeing is that we're getting astronauts not just from America and Russia, but from countries all over the world. And of course, this is a fantastic opportunity for us because in November this year, on Friday, November the 20th, British astronaut Tim Peake will be launching to spend 6 months on the International Space Station. He'll be doing all sorts of scientific investigations. My team have developed some of the experiments that he's going to be doing, and I'll be delighted during the mission to come back and to give you some updates. And he's going to be all over the news, probably from about September, October onwards in preparation for his mission. So we've got a great opportunity to showcase what we do in Britain. Now, you know, for me, and I think for many of you, the idea of humans going into space exploring, you know, it's inspirational. And we need to remember that it's not just humans. We have sent our robot explorers throughout the solar system. Our great telescopes in space, like the Hubble Space Telescope and the Chandra Observatory, they have seen back, literally, to the beginning of time itself. We have seen out, virtually, to the edges of the visible universe. And what we've learned is absolutely mind-blowing. But of course, not everyone thinks like that. Take Davina McCall, for instance. We know her because of her television career, but she has gone on record many times as saying space science is an absolute waste of time. Why do we bother with it? What difference has it made to her life? Now, much as I violently disagree with her opinion, it's a good question. What difference does it make? I'd love to get the opportunity to actually meet with her, because if I did, I'd say to her, look, Davina, if it wasn't for space science and space applications, you would not be a multi-millionaire. Why not? I mean, she hates it, but why has she got to thank space for being a millionaire and making all the money that she does? I'm assuming she's a millionaire. Yes.
Because of the TV antennas.
Fantastic. Not so much the antennas, but specifically those little side dishes on the side of your house. We forget that if we've got satellite TV, I know the word satellite is in there, you're relying on a signal coming down from a satellite
35,800 kilometres above the surface of the Earth. And there's not just one of them, these are telecom satellites. Earth's got a ring system of these, hundreds of these, and hundreds of other ones. And the fact that we can now get live sports coverage and news coverage from around the world almost instantly has only been possible because of the development of telecommunications satellites. And what about GPS? We all know about sat-nav, we've got them in our cars, we've got them on our handheld devices, and occasionally we curse them when they take us the wrong way up a road. Okay? I must say, it's not a problem with the GPS satellite, it's a problem with the software in your handheld unit if that happens. What people don't realise though, is every international bank transaction in the world is measured by time against the atomic clocks on these satellites. So if I was to magically switch off all of these satellites and all of these satellites right now, life wouldn't come to a halt. But our way of life, in terms of information and finance, would grind to a halt in about a day and a half. We need all of this information from space. But there's far more than that. Space science is actually saving lives every year. This is an image that I didn't show you when I came for the observatory opening because it was from October 2013. I remember this because this was actually the day I got married. This is a tropical storm, a cyclone called Cyclone Failin. And it developed in the Indian Ocean. Here it is, and here it is at landfall. Now this was monitored for about a week by satellite, so the meteorologists knew where it was going to hit the Indian coast. To give you an idea of scale, England is about this big, okay? Because this is a monster storm. They knew where it was going to hit. They evacuated people from around the coastline. Tragically, about 200 people died, but thousands were saved. To give you an idea, in 1970, a similar sized storm hit the Bay of Bengal, hit Bangladesh here, and 1 million people died. Because we didn't have enough monitoring of the weather from space to know where that storm was going to hit. So weather satellites are saving thousands, hundreds of thousands of lives every year. And it's not just looking at the clouds the way that the human eye would see. We use all sorts of other, what we call wavelengths of light. There's a whole lot of light that the human eye can't see. And I want to show you what happens when from space you measure the Earth in infrared. Infrared, many people think of it as being heat radiation. That's a bit simplistic, but it turns out if you've got an infrared thermometer in space, just like the ones you might monitor your baby's temperature with, by how many of you know those sort of thermometers which you point them at something, you press the button and you get a temperature reading? Effectively, you take a high-tech one of those, put it on a satellite, and you can measure the temperature of the Earth's oceans. This was an instrument that did that, a British instrument, the Advanced Long Track Scanning Radiometer, which is just up here. And this is the satellite that created the data that I'm going to show you now. It's a beautiful image, but it's full of lots of science. Now, what you've got on the left is the time from 1993 to 2004. What you've got on the right is the temperatures in degrees Celsius, and we are going to look at the temperature of Earth's oceans. What I want to start with is look at where we are now. We are at the same latitude, the same degree north as northern Canada. And in northern Canada, every year at winter, they get 4 months where they have meters of snow, and their summers are really, really hot and humid. They have much more extreme weather than us. The only reason that we don't is because of a warm water current called the Gulf Stream, the North Atlantic Drift. And so understanding the oceans is really powerful if we want to understand the climate. Now we're going to go through 11 years of space temperature measurements for the oceans. It's incredibly beautiful, but there's so much science here. I'm going to take a bit of a tour. Look at how the polar caps get bigger and smaller during winter and summer. And as we change our perspective, we're now going to look towards Antarctica. So you can see these warm water currents powering the weather systems here. It's the oceans that power so much of our weather systems. Look at how big Antarctica gets every winter. Their winter is in June and July. The continent almost doubles in size. Look at this. And then, of course, during the Antarctic summer in December, January, all of that ice melts. And if we change our view and start to look at the equator, every single one of these tiny
tiny little swirls has got huge amounts of energy. That's what powers global thunderstorms and global cyclone systems. And of course, any change to these currents is going to have a massive impact on our weather. Is climate change real? Yes, absolutely. How much of it is being caused by human behaviour and human activity is what we're still unsure about. But having these satellites looking at Earth are giving us major new insights into understanding things. And of course, in Britain, this is one of our best kept secrets. We are world leaders in so many different aspects of space science. These are the numbers. And for every £1 that the government spends on space, we get about £8 or £9 generated for the economy. So we've got tens of thousands of people involved, and we need more people to come into our space business. So I'm looking at the young people in the audience especially, but not exclusively. I didn't come into the space sector until about eight years ago as a late career change. And so basically the UK Space Agency needs all of you if we want to keep our space activity going. But I want to move to something much more dramatic now, which is this whole idea about whether space science could actually save life on Earth. The answer is yes. And if we want to know more, we need to understand all about comets. Now, I know that we have some astronomers in the audience, but could you put your hands up, please, if you've ever seen a meteor or a shooting star? Okay, most of you have. So you see a speck of dust, a tiny speck of dust, that hits the Earth's atmosphere, burns up in the atmosphere, leaves a trail of waste for, stays there just for a few seconds. Shooting stars aren't the same as comets. If you see a comet in the night sky, what you'll see is what looks like a star, but it wasn't there before. And night seen them throughout history, around the world. Here we've got a scene from 1066, the Bayeux Tapestry, Battle of Hastings. There's Harold and his followers looking to the sky in absolute terror, because that year, Halley's Comet, the most famous comet of all, put in an appearance, and no matter where you go around the world, comets were always associated in superstition with like death and destruction. What I want to do is try to understand what science has taught us about comets. Now, before we actually build a comet nucleus here in the lecture theatre, just a couple of things about comets. They're part of the solar system, but they don't have the orbits like planets do, which are nearly circular. They've got very, very elliptical orbits. And what that means is most of the time, comets are in the outer wastelands of the solar system, where the temperatures are incredibly low. This is material left over from the formation of the solar system. So if we can understand comets better, it's a little bit like doing astronomical archaeology. We can perhaps understand how our solar system formed, and possibly understand about the origins of life as well. Comets generally come from two different categories, what we call Kuiper belt comets and the Oort cloud. I'll talk about that later if people want more details. But in terms of what a comet actually looks like, this is one of the most spectacular comets of recent years, Comet Lovejoy. This image is taken from the European Southern Observatory in Chile, and you can see it here. This image was taken by a NASA astronaut, Dan Burbank, on the International Space Station. And it's interesting because Dan has spent a total of nearly 200 days in space on 3 missions, and he says the most spectacular sight he saw ever in space was Comet Lovejoy from the International Space Station. But what I want to do first of all, this is the tail of the comet. The business part here is the nucleus. It's absolutely tiny, which I'll talk about in a minute. I just want to talk about how far the tail of a comet can actually stretch, and you might be amazed at what the maths will tell you. Before we do that though, I need a volunteer, and at the beginning of the lecture, David did volunteer because he was here really early. So David, will you be my volunteer for this? Can you give him a round of applause please, because he has no idea what he's doing. Now first of all, I just want to show you, this is a picture of the Earth and the Moon. This is a lovely shot taken by a spacecraft called Galileo. It's not really that close. Okay, this was what we call a perspective shot. So it was like the Earth was here and the Moon was here and you were the Galileo spacecraft and they were lined up. And the trouble with this sort of picture is it doesn't get the scale right when we look at the size of the Earth and the size of the Moon. So what I've got first of all is I've got a simple demonstration to show you
what the language of maths actually tells us about how far away the moon and the Earth are. And we're then going to apply that to comets. So this is the moon. When I look at the moon, it's about the same width as Australia. 2,160 miles in diameter, for those of you who are old-fashioned like me and remember things in miles. So next time you look at the moon, it's the size of Australia. Now if we take the Earth-Moon distance, it's roughly 10 times around the Earth's equator, about 240,000 miles, 384,000 kilometres. So I've wrapped a bit of string around here 10 times. David, would you mind just grabbing this? And would you start walking back to this? And you stop. This is the sort of picture that we get in textbooks, and many of us think, oh, big deal, the moon's not that far away. There's a lot of string left here, so let's keep going. And if you haven't seen this demonstration before, I think you're going to be quite surprised. And, careful David, we've got some chairs behind you, so if you stop there and I'll keep going, you might be quite surprised at what the language of maths actually tells us about the Earth-Moon distance. This is the true to scale distance from the Earth to the Moon. The boundary of space, how far away did I say it was? 100 kilometres, 62 miles, that's 1 millimetre on this scale. The International Space Station orbits at 400 kilometres on average, that's the width of my finger. And this is our nearest neighbour in space. So, first of all, you now hopefully have a better picture of the Earth-Moon distance. We're now going to apply it to comets. David, thank you very much. Can you give me a round of applause, please? Okay, I've got to thank one of my colleagues, Professor Ian Wright, who is principal investigator for 3 of the instruments that are on the Rosetta mission, because this explanation is his idea. This is the nucleus of Comet Lovejoy, this is the coma and this is the tail. That's the comet that you saw before. There's the Earth to scale, so the moon will be about here. This slide is 1 million miles wide. How far would that tail stretch? Not just one of these slides, but I'd have to have 150 more slides to show how far that tail stretched. It stretched across the inner solar system. And so, although the tails are incredibly thin material, okay, comets, you can start to understand now why they are so spectacular when you get a classic one like Lovejoy. Now, what about the nucleus? This is the business part of the comet. Well, there's this great technique we use in science called spectroscopy, and it's a little bit like optical fingerprinting. What it means is you can look at the light coming from an object elsewhere in the solar system or elsewhere in the universe, compare it to the light that you find in the lab, given off by certain elements. You can match up the light and you can work out the chemical makeup of something, even though you never touch it. And when that was done with comets, the results was absolutely staggering. This was first done more than 100 years ago. And what we found is the material in comets, especially these organic compounds, complex compounds with carbon in them, they're very often the materials we find here on Earth. And all of this means that we can build a model of a comet nucleus right here in the lecture. And that's what I'm going to do now. It can get a bit messy, so I'm going to be, it's probably the only time in my life I actually put on a lab coat. My wife will kill me if I trash my shirt again. And I'm just going to talk you through the makeup of a comet. Every ingredient I put in this bowl, because this is what I'm going to make a comet in, has got the chemicals that we have found either spectroscopically or through direct sampling from a real comet. I'm not making any of this up, honest. And with 1 or 2 of these ingredients, I will have some raised eyebrows, I know. First of all, what we found was that comets, let me just move my stuff out of the way here, comets are very rich in water. I mean, you can play the game of identifying the compounds, of identifying the compounds that we have up there, and somewhere on the screen, I'm going to try and multitask and fix my clicker, somewhere on the screen we'll see good old H2O. Clicker, please work. Yes. Where is it? Up there. So what I'm going to do first of all is I'm going to put some water into my bowl. This is just a bin liner and a plastic washing up bowl. Okay. Next thing I'm going to do, comets are really rich not only in carbon compounds, but in carbon, element number 6 of the periodic table itself. So I've got some carbon powder, very dark, I'm going to whack all of that in. Comets are also really rich
in what we call silicates. That means ground up rocks. So I've got some sand, whack it in the bowl. But this is the part where the eyebrows usually start to get raised. Why has he got a bottle of red wine here? Well, I could have brought a bottle of vodka, but I thought that's not setting a very good example. Comets are rich not only in ethanol, but in other members of the alcohol family. Methanol, butanol, propanol, and so on. So what I'm going to do is pour in some red wine to represent the ethanol content. Even more amazingly, we found that comets have lots and lots of amino acids in. Amino acids are the building blocks of life. And amino acids are what give Liam Perrin's Worcester sauce its classic smell and its classic flavour. So, I'm adding the amino acid content now. But of course what makes this demonstration really special is the final ingredient. You'll notice I'm missing out lots of stuff, so this is going to be a Comet analogue of sorts. For the final ingredient, I want you to focus in the top left corner, because comets have got carbon dioxide in, but that carbon dioxide is not in the form of a gas. Do you remember I said comets spend most of their time in the outer wastelands of the solar system, where the temperatures are really low? Well, the thing with carbon dioxide is the gas that we breathe out is that on Earth, if you cool it to minus 78 degrees centigrade, it freezes solid. It forms what we call dry ice. So what amazes me about how I'm going through this demonstration is that this dry ice is the gas, but a frozen version, that you breathe out all of the time. But this is colder than virtually any place on the surface of the Earth. A couple of places in Antarctica get down below minus 78 in the middle of their winter, but not for very long. So I'm going to add my carbon dioxide to the mix, but this is where, I always think of it as a bit of sort of Harry Potter effect, but this is where the problems can start for me, because when I put this into here, I'm going to get something at minus 78 degrees centigrade going into the water, trying to expand hundreds of times in volume. But at the same time, that water is going to try and freeze and form a cage of ice to imprison the carbon dioxide. So this is where we can get something called explosive outgassing. This is where it can make a real mess. And this is why, every time I do this, I have to say, I apologise in advance, Jim, if I end up making a real mess on your table. That's why I brought these paper towels. So, without further ado, I'll start adding my dry ice. And you can see this fantastic effect here. What's actually happening there is water vapour from the air is condensing and cooling down. Put in a bit more. Add a tiny bit more water. And while I'm mixing it, this theoretical model of what lurks at the heart of every comet nucleus was actually first dreamt up in the late 1940s by an astronomer called Fred Whipple. And when he put together his theory, he called it the dirty snowball model. Put in a little bit more, give it a bit of a stir. And what I'm going to try and do now, a tiny bit more water. Every comet nucleus that I make this way is slightly different. You can see how the gas, carbon dioxide is sliding away. So this is where I'm going to try and push all of these ingredients to form one congealed lump. Oh, that's a really nice one. Let me just leave it for about 30 seconds to form up, which lets me clean up a bit of my mess and hopefully avoid getting in too much trouble. Okay. Now, as I say, this was a theory that was first proposed in the 1940s. And even though astronomers knew that all these substances were there, many of them still couldn't get their heads around the idea that a comet nucleus could end up looking like this. Because when I extract it from the bag, this was Fred Whipple's model of what is at the heart of every comet nucleus. And wow, this is a biggie. Okay, pull off that bag. Extract it from there. That was Whipple's model of what is at the heart of every comet. And his theory was that as they approach the sun, all of this material will start outgassing, and you can see there the gas jets that are forming as a result. It's incredibly dark, which is one of the problems with astronomers thinking, no way, comets can't be this dark. And of course, although Whipple proposed it in the 1940s, I'll leave this there, so if anybody wants to have a closer look later on, they can do. In the 1940s, when Whipple proposed it, there was no way you could get close enough to a comet to actually have a look. We had to wait until 1986 to do that, and this is where Europe beat the Americans. Because in 1986, the Giotto mission flew by the nucleus of Halley's comet, and this is what it saw. One of these, the size of Nottingham. This is about 15 kilometres by 12 kilometres by 9 kilometres. You can see there, if I just go back and forwards again, you can see as it tumbles away, as it approaches the sun, all of that material starts outgassing, and it's this material that goes to form the tail of the comet. Now, if we're looking at the orbits of the comet, one of the things that concerns people is what are the possibilities that comets, look at the orbits crossing the paths of the planets, what are the possibilities that a comet could actually collide with a planet? One thing I do want to say is that when I was a child, comets were regarded as being really different from asteroids. Asteroids were lumps of rock, comets were giant dirty snowballs. What we're actually finding is there are some comets that are definitely comets, and there are some asteroids that are definitely asteroids, but there's some objects that seem to be a mixture of both. There are some comets that are quite rocky, and there are some asteroids that are quite icy and gassy, for want of a better term. But whichever way we look at it, when we look at these orbits, be it for asteroids or comets, some of them do cross the orbits of the planets. And to answer the question whether or not we ever get hit, I want us to turn our minds back to the day after Valentine's Day in 2013. On this particular day, there was an asteroid, a bit bigger than a space shuttle, that we knew was going to pass the Earth within about 20,000 kilometres, and it was going to miss. And we all knew this, some of my team were involved in tracking this, and nobody was worried. But in one of the biggest coincidences ever in astronomy, on that day, a completely separate object that nobody had spotted because it was coming from the direction of the sun, came in and entered the Earth's atmosphere over the city of Chelyabinsk in Siberia. And this is what 1 million people in Siberia, waking up on a Friday morning, saw. A fireball streaking across the sky in total silence, getting brighter and brighter and brighter until it was brighter than the sun, leaving this churning tail across the sky. And as I say, that was in absolute silence. It struck complete terror into hundreds of thousands of people. And this is what it was like on the ground. You might want to cover your ears if you don't like surprises. So in total silence, they're seeing that. Many of them were thinking, is it an alien, UFO, is it World War III? Exploded about 30 kilometres high. The blast wave was detected around the world. Because of all this data, we now know how big this object was. About 20 metres in diameter, travelling at 15 or 16 kilometres a second, and energy-wise, that explosion was equal to 20 Hiroshima bombs. If that had actually detonated on the ground, it would have destroyed the city of Chelyabinsk with 1 million people. We had a very lucky escape on this day. And there's a representation now of the object that missed us on that day, 2012 DA14, and that's the size of the Chelyabinsk object. Pretty small, but of course it's travelling so fast that when you do the physics of what we call kinetic energy calculations, this is an incredibly large amount of energy. And to answer the question, well, do these objects ever get to the ground itself? Do we ever get craters? Just want to show a few of my home pictures from a few years ago on a holiday that I went on. You might think, why has it got a mine shaft here, a cardboard cut out astronaut? Let's zoom out. We've got a mine shaft, we've got a range of hills, but actually it's not a range of hills. This is the most famous crater of all that was produced by a meteor impact or an asteroid impact. It's called Meteor Crater. It's about 3/4 of a mile wide, it's about 600 feet deep, and it's in northern Arizona. This is what happens when 100,000 tons, or about 200,000 tons, of iron-nickel asteroid smashes into a desert. And this was the energy equivalent of a hydrogen bomb. About, let me think, 100 Hiroshima bombs going off. And there are fragments of this all over the desert floor. It's incredibly dense material. Now, that was 48,000 years ago, but there have been other events even in the last 100 years. 30th of June 1908, there's a mystery explosion over Siberia, in a place called Tunguska, that flattens the forests for 25 kilometres in all directions. These pictures were taken 20 years later, when an expedition finally reached that site. That was a comet nucleus, a very small one, exploding in the atmosphere. And if that happened today over central Coventry, it would destroy every building all the way out to Nuneaton. And so here we've got a representation of some of the objects that have created some of the famous impacts. And of course what we're worried about is not so much the objects that were the size of Chelyabinsk. I mean, if that had hit the city, it would have been a bad day and it would have caused tremendous devastation. But this sort of object is not going to cause global climate change. The objects that we're worried about are the objects that are more than half a kilometre across. Because when these objects hit the Earth, they have global consequences in terms of what they can do. Firstly, you get a massive crater blasted out that could be hundreds of kilometres in diameter. All that hot material goes up into the atmosphere, some of it goes out into space and re-enters the atmosphere. You can get global firestorms, and we've got geological evidence of that. But of course, if it smashes into the Earth's crust and blasts all this material up, that material going into the atmosphere can cause chemical changes which can result in enormous amounts of carbon dioxide being released. And then, of course, if you've got temperatures going up and then you've got global darkness because of all of this material going into the atmosphere, blocking out the sunlight, if you remember about food chains, kill off your plants and everything above the plants in the food chain will die out as well. And so these objects hitting the Earth can have global consequences. And of course, 65 million years ago, an object about the size of Nottingham, a comet nucleus, smashing into the coast of what we now know as Central America, Yucatan, was one of the factors that led to the extinction of the dinosaurs. And of course, in my lifetime, we've seen what happens when a comet smashes into a giant planet like Jupiter. This comet, Schumann-Levy 9, was a really unusual one because it was 21 fragments of dirty snowball. This is the biggest one, the G fragment, about 3 kilometres across, so a small one. It was unusual because it wasn't orbiting the Sun. This comet was orbiting Jupiter. It had been captured by Jupiter's gravity. And finally, it was unusual because a year after discovery, we realised that on the 16th of July 1994, all these fragments were going to smash into Jupiter. We were going to see these sorts of impacts in real time. And it's fair to say that the astronomical community split into two camps. People like me were thinking, we're going to see the biggest energy events that humans have ever seen. And yet there were other astronomers who said, hold on a second. This is like 3 kilometres across. Jupiter, you could fit 1,000 Earths into. This is like a fly charging into a rhinoceros. We're not going to see anything. So I'm now going to show you what we saw when all these fragments smashed into Jupiter in July 1994. That's the fireball of the G fragment. There's the fireball of the previous fragment. This is an infrared image. Those are the scars that were left in Jupiter's atmosphere. That's the scar that was produced by the G fragment, and it remained as a scar or as a feature in the gassy atmosphere for about 3 or 4 months. On this next slide, we're actually going to superimpose this onto the Earth.
If that had hit Earth in July 1994, it possibly would have wiped out 30% of life on the planet. So these sorts of events do happen. But before you get too worried, events like this only happen on Earth once every 10 or 20 million years. So I don't want you to worry yourselves too much. The importance of the space side of things is, of course, some of you will remember these classic films from the 1990s. Bruce Willis and his oil workers saving the world in Armageddon and Deep Impact. These were Hollywood films about what we could do if a comet or asteroid were heading our way. Could we deflect it? Could we somehow stop an enormous mass extinction event? That line's a bit tongue-in-cheek. It's from a science fiction writer called Larry Niven, but it's absolutely true. We are the first species in the history of life on our planet. If there's an object out there heading our way, we could do something about it. And there are all sorts of strategies, including trying to blast it to smithereens, that actually doesn't work, or deflecting it out of the way, that could give us a fighting chance. And so space science might have a future role in preventing a mass extinction